Now, we can go through this through the motions here, but we've gone through these calculations very carefully in just the previous segment. We had just, the only difference was that instead of the function psi, we had our special function, the mass density in the spatial configuration rho. The operations are all the same otherwise, okay? So where this takes us is the following. We get now integral over omega naught, okay? That first integral is essentially what we've sometimes called this, okay? The substantial time derivative, all right? Times j plus the next, oh sorry, it's not rho. I'm thinking back to our previous segment. It really is psi here, okay? Plus we have psi, function of little x and time, j dot, right? And j we observed last time was, j dot we observed last time was just j, divergence of the spatial velocity, okay? Right, and I've introduced this here, but let's just remember that this is after all just this time derivative all right, okay? But then we also remember that this is just partial of the proper partial time derivative of psi plus the convective term. Okay? All right? Okay. So putting all of this together, we end up with a term, with an integral which looks like this. Partial of psi with respect to time plus. Now, this term, okay, is multiplied by j, right? And then we have this term here, right? Both of those can be combined to write divergence of psi v, okay? All of this multiplied by j d capital V, all right? And finally, we change variables back into the current configuration, okay? So now we say change variables again to omega sub t, right? And x comma t. Okay? What that means is that we go back to changing the domain of integration, right? So what we get then is, remember all along we were trying to compute d dt of it. All right? So what this does for us now is to say that, all right, we can write this integral once again as an integral over omega t, okay? We have the proper partial time derivative of psi plus this divergence term, right, acting on psi times the spatial velocity. Now, j d capital V becomes d little v, okay, because j is the ratio of the current to the initial elemental volumes, and dv is the initial or the reference elemental volume. Okay, so that product gives us the current or the deformed elemental volume d little v. Okay, so all of this becomes integral d little v. Okay, and we're essentially done. Also observe that in this final step we have rewritten the integral as it was presented to us originally as 1 over as an integral over the current configuration, right, over the spatial configuration. Okay, so this trick of changing variables, putting things back into the reference configuration, carrying out our derivatives there, and then, so to speak, pushing things forward is a very common one in continuum mechanics, and it's something that we will use repeatedly. Okay, so at this point this may look rather abstract, but let's straight away give you a special example of it. Okay, so as an example, let's actually go to the connection we've been making earlier. Okay, so as an example, let's suppose that psi of x comma t is rho of x comma t, okay, which is the mass density okay in the current configuration, right? So that would be mass per unit current volume. Okay, it's the quantity that we were working with in the segment just before this. Okay, so in that case, I comma t, let's think of what this is. This is the integral that we started working with, right? This quantity that we started working with is now right? That integral on the extreme right is simply what? It's a fundamental quantity, fundamental physical quantity, right? It's the mass, exactly. It's the mass of the body, right? So the body starts out in its reference configuration, right? It deforms, goes into a current configuration, right? There's some deformation, but a point we made very early on is that in our treatment of continuum mechanics, if we are ignoring chemistry and some transport processes, mass stays fixed. Okay, so that's the quantity we're trying to evaluate here. We're asking, well, what happens if we choose psi to be the mass density? What's happening to this quantity I? Okay, so we observe that this is just the total mass. Okay, and so d dt of I comma t equals, okay, this is the total mass, let's call it capital M, all right? So d dt of I comma t is just d dt of M, okay, because it's fixed, that has to be 0, okay? But now, if we apply our result from Reynolds transport theorem, what we get from Reynolds transport theorem, what we see is that d dt of M is now integral over omega t, this partial time derivative plus the divergence of rho v. Okay? In the previous segment, the quantity in parentheses here, okay, was, so to speak, the left-hand side of our conservation equation, conservation of mass equation, okay? And we demonstrated there through other means, right, by considering what happens with the reference density, we demonstrated that this quantity in parentheses that forms the integrand of this right-hand side is actually identically 0. Okay? Okay, and we showed this. Okay, we've already shown this. Okay, and so everything works out, right? We do expect from the previous line, we do expect that the mass is going to be conserved, right? We have this physical idea of the mass being conserved, and we've already seen this result. Okay. So this is indeed equal to 0, checks out. Okay? So that's an example of how the Reynolds transport theorem is actually used. Okay? We're going to take a break at this point and start a new segment when we return.